Our final paper for this session discusses some congestion control methods on the switch side. So this will be a remote presentation by Liang Chengyu, who is a rising fourth-year PhD student at the University of Pennsylvania. His current interest is in in-network computation and control with emerging hardware accelerators. So after the talk, one of the courses, Vincent, will be able to do a live Q&A here in person. So let's play the video.
Today, I'll be presenting Cebinae, a scalable mechanism for augmenting fairness in public networks. This is a joint work with John Sonjak and Preston and my advisor, Vincent Liu. For public networks like the internet, end-host applications can use any congestion control protocols they wish, and the traffic may experience diverse paths varying in the number of hops and RTTs. This heterogeneity is only increasing as the public networks evolve, partly due to the diverse application requirements for the underlying transports, but also its nature of decentralization and autonomy. As a result, public networks care about fairness by some definitions in order to prevent potential application performance impact. For example, for victim flow, if another application flow has a different RTT or uses a different implementation of congestion control algorithm, the victim flow may suffer from performance degradation whenever contention happens along its path. To enforce fairness, one approach is to rely on the end host. For the similar reasons underlying the diversity of public networks, implementing fairness control at the edges is challenging. While one might come up with an end-host mechanism that overcomes unfairness, it is infeasible to deploy the same protocol across the whole public network. Similarly, it is also hard to apply changes across the whole network where there are diverse hosts and applications. Fundamentally, there are also few incentives for hosts to prioritize others' fair share or TCP friendliness, and even fewer penalties if they fail to do so or choose not to cooperate. In the end, when fairness is desired, the only incentive comes from network operators of the in-network devices. Luckily, there have been many proposals on in-network support for fairness. One of the most classical approaches is fair queuing, which presumes independent per-flow queue and the service of the queues in a round-robin manner. However, the existing approaches often suffer from limited practicalities due to their strong assumptions on specialized hardware, cooperative congestion control behaviors and the end host, and so on. One exception is approximate fair queuing, which is the first to show how to approximate per-flow fair queuing on today's programmable switches. While AFQ made a substantial step for practical fairness enforcement, it still suffers from scalability issues such as the restrictions of the exclusive use of priority levels, the number of physical queues, and the stringent requirements on the amount of usable buffer for each flow when there's a higher number of flows, network bandwidth, and RTTs. In the end, existing solutions still have difficulties scaling to public networks using today's devices. We know that a primary source of this difficulty is that these approaches attempt to track and schedule each individual flow for fairness strictly on per-packet basis. In this paper, we propose Cebinae, a simpler approach to in-network fairness. Instead of targeting fairness at the byte or packet level and at every instance in time, Cebinae redistributes the bandwidth of flows that exceed the max mean fair share to those haven't. While this gradual redistribution process relaxes the rigid guarantees of fairness in fair queuing, it preserves the similar capability of mitigating unfairness in practical settings. Further, this simplification enables efficient approximations of advanced in-network computation modules. In this slide, Cebinae enforces a binary taxation mechanism that presumes no modifications to edges, deployable on today's programmable switches, and has a high coverage of supported congestion control algorithms. For the rest of the talk, I will start with introducing the conceptual foundations that inspire Cebinae's design before going into Cebinae's detailed taxation operations and evaluation. Here's a classical definition of max-min fairness. Essentially, a max-min fair allocation has a necessary and sufficient condition that for every flow, we could find at least one bottleneck link such that the link is saturated and the rate of a flow is among the largest of the flows sharing this link. That is, one could verify max-min fairness of a network in a distributed manner. Specifically, each link can determine the set of bottleneck flows per definition. If a link is not saturated, that means all flows are not bottlenecked by the current link. Otherwise, a flow is considered bottlenecked if it has the largest rate. Cebinae is based on two observations. The first is that each of the possible cases can be differentiated using only link local information. Example, the byte counters for the port. The second is that this process involves a classification of only two groups, bottlenecked and non-bottlenecked, which renders more efficient implementations than those requiring more fine-grained differentiation. One naive enforcement is for every switch to detect the saturation status of the links, and if the link is saturated, rate limit the flows with largest rates by dropping packets based on their current rate. Intuitively, this is similar to the water filling process, which operates by finding the bottleneck link for each flow and then setting the back bottleneck flow to constraint state while other flows continue to increase. However, there are several problems. The first is that while this approach prevents the flows from taking additional bandwidth unfairly, it can't make an already unfair allocation fairer. The second is that today's congestion control algorithms have become diverse in the signals they leverage. Algorithms may operate on non-loss signals and are less responsive to this rate-limiting approach. Therefore, instead of simply operate on drop reactions, Cebinae targets a penalty box that can enforce both loss, delay, and other congestion control signals. Second, instead of using the last known rate for the bottleneck flows, Cebinae attempts to collectively redistribute a configurable fraction of their bandwidth to flows that haven't reached their fair share. The graph here illustrates the ideal Cebinae operation, which taxes a portion of the bottleneck flow bandwidth to non-bottleneck flows that are potentially bandwidth starved. Cebinae instantiates the idea using a per-router architecture that can be considered in isolation. At the high level, the architecture serializes three components seamlessly. The first is the egress pipeline cache that tracks the rates of bottleneck flows at a fine granularity. The second is a leaky bucket scheduler that enforces taxation at the ingress pipeline to cap and redistribute their bandwidth. Lastly, a low-latency control plane agent pulls the states from the egress pipeline and dynamically adjusts the bottleneck flow membership and reaccounts their rate limits. In the next few slides, we'll walk through their detailed operations in the context of a typical flow's lifecycle and highlight their features. When a packet arrives, the first step of the operation is to classify its membership either as bottlenecked or non-bottlenecked. Then, the leaky bucket filter accounts for the budget of sending bytes based on the membership classification. Cebinae's leaky bucket filter mechanism draws inspiration from calendar queue-based invariants, which are capable of injecting both loss and delay signals. However, Cebinae makes several innovations to ensure its practicality and scalability. For instance, instead of enforcing a static, per-flow fairness with a deep set of calendar queues, Cebinae implements dynamic rate enforcement with only two flow groups, and therefore two physical queues. If the packet's time schedule falls within the range of the current time horizon, it will be placed into the head queue. If the packet consumes the future budget of the next round, it will be placed into the non-head queue, which is of a lower priority. Note that leaky bucket filter is configured to guarantee that all of the switch buffer is available at all times, regardless of the connection sending patterns. Therefore, a leaky bucket filter can safely drop the packet if the packet continues to exceed the current budget. Finally, the packet enters the egress pipeline and updates the traffic counters. In order to prevent exacerbation of the unfair allocation, Cebinae uses hash-based flow tables. They are optimized to minimize false positives. Instead, false negatives are tolerable as those bottleneck flows will simply compete with other flows as they do today. Cebinae also executes reconfiguration per round triggered by the data plane packet generator. The control plane rotates the priorities of outdated, empty head queues to continually generate low priority queues for future traffic. Cebinae guarantees no reordering of the packets or violation of the queue draining deadline using virtual pacing techniques. Finally, the agent updates the classifier and clears up the leaky bucket filter budget for the last round and resets the caches via atomic transactions. Cebinae keeps executing these operations to dynamically determine the port status and bottleneck flows and apply bandwidth shuffling accordingly. We implement the Cebinae prototype on Tofino 1 switches and also NS3 modules. Using this implementation, we found that Cebinae can effectively mitigate unfairness under various network conditions while using minimal resources, such as only 2 queues and priorities. The paper contains more detail, and here we look at a few of these cases. As a preliminary example, the graph here shows the case when 16 TCP Vegas flows, which operates on delay signals, compete with one neuronal flow, which reacts on lost signals. While each flow has the same RGTs and demand, without Cebinae, the single neuronal flow consumes around 80% of the bandwidth, as shown by the bars colored in blue, causing a case of persistent unfairness. With Cebinae, however, it mitigates this skewed, unfair allocation by significantly improving the James Fairness Index. The CDF graphs here illustrate the distribution of good puts for another 2 contending scenarios. As shown by the figure on the left, Cebinae prevents the greedy behavior of aggressive flows, as reflected by the removal of the long tail in the original blue curve. Similarly, Cebinae also mitigates starvation towards the smaller flows, as reflected by the more centralized distribution in the CDF with Cebinae effects. We further validate the performance of Cebinae under a diverse set of network environments, including variances in RTTs, congestion control algorithms, and so on. Each row here illustrates an instance of persistent, unfair allocation and Cebinae's effects of mitigating unfairness without loss of efficiency. It is clear from the table that Cebinae is agnostic to the end-host congestion algorithms, as fundamentally, Cebinae treats them as black box and is agnostic of their concrete implementation. To summarize, Cebinae is an attempt to scale in-network fairness augmentation mechanism to public networks using only commodity programmable switches. We show that Cebinae uses minimal resources due to its significant simplification while maintaining the capability of mitigating persistent unfairness. The code is open source, and thank you so much for attention.
Cool, thank you. It seems that the congestion control algorithm actually works because Liangchen is online to give a live Q&A. So can we cut over the video? Okay, fortunately, we have a fallback. So maybe while we're waiting, people can ask Vincent questions. Okay, maybe I will start. So obviously, this algorithm depends on the capability of changing the switch, right? And in deployment, how would you imagine that this would be deployed? Let's say in the data center environment, would it be deployed as a top of rack switch or as or any place within the path?
Yeah, so it's a good question. So I think in an ideal world, you'd have Cebinae deployed at every switch. I think that's what would give you kind of the closest approximation to a max-min fair network. If you wanted to do a partial deployment, that's fine too, right? So I think kind of one of the key ideas here is that we're not shooting for perfect fairness. We're just trying to mitigate or tax the most kind of persistent unfairness, persistently unfair flows. So it still benefits.
Anja Feldman, one question I have is how do you scale this to a setting where you have hundreds of thousands of flows, of which 90% are short flows, less than 10 packets? Got it.
So I think so one of the really interesting things here is that you have essentially only two classifications, right? So as opposed to prior work, we kind of merge all those things together, and that gives us actually better scalability and the ability to handle cases exactly like that, right? So if you have a bunch of small flows together, I think you'll just aggregate their aggregate their reserved throughputs, and it should be fine. Yeah, there's going to be a follow-up.
But doesn't that require per flow state, and how are you going to keep that? Because
right.
You need to know that a flow is short.
Right, so I think, how should I say this? So it doesn't require per flow state because of the properties that we're trying to target, right? So one of the really interesting things that we realized about max-min fairness is that it doesn't matter what happens except to the largest flow on each switch. And so that should be...
But how do you find your largest flow?
Okay, fair. So that does require per flow state, although it only requires per flow state for the largest flows, right? So if 90% of your flows are small, it's not going to...
So maybe we
anyway,
can take that offline.
Yeah, we can take this offline. But I think we do leverage prior work on this type of kind of bandwidth accounting, and those works tend to be more effective for large flows, which is what we're targeting.
Okay. Cool. So that concludes this session. Let's thanks our speakers again. Yeah. So, thank you.